So this is where we last left off. We're now going to learn, no it's not, it's kind of dark. We're now going to learn how to utilize the rules, and this is what we were given, and try to piece together and determine the structure from that. And like I said, a lot of people have a lot of fun with this in the sense that it's like a jigsaw puzzle or a mystery or something like that in that sense. The problem is usually on a quiz or an exam, you don't have, you're limited in time. So I say practice, practice, practice. I want you to know the simplest ones, the whole idea of j+1. I want you to understand the logic behind all the others, but in the sense that some of the most complicated ones I wouldn't expect you to draw necessarily. There is just one or two exceptions I'll point out along the way that are really important biologically. Okay, so first off, we had to do the RDB, which remember whenever we did the RDB, and I'm not about to try to type that all out, it'll take me forever, it was equal to 1. So remember that was we had to go in order. So we had the RDB for rings double bond equation, and it said that there was 1. Something there was either one ring or there was a double bond, and we had already talked about logically how it made sense that it had to be a double bond. Because since there are only 4 carbons, there would be no way to put those 4 carbons and the oxygen together as a ring and have it meet up with these spectra. Okay? And then number 2 on our little checklist was, if I remember right, I said check the IR, which the IR here was given. The IR showed that there are no alcohols. And sometimes you don't have that luxury. Of course, in lab this week, hopefully everyone got the chance to use the IR. The IR spectrophotometer, it's really cool. It's really obvious usually whether or not there's an alcohol present or carboxylic acid present. All right, so this was already told you that IR showed that there's no alcohols. Then 3, and this is the really important part, you need to go in this order. Because if you go out of order, it's going to make your life much more difficult. 3 was we had to look at the total number of signals. Okay. And so here, because what did that tell you in general? Remember we had signals, and what did the signals indicate? They indicate something very important. So first of all, in this example here, how many signals do we have? 3. So that tells you that there are 3 types of hydrogens or protons that are available. Some of these may be identical, but there are 3 different types that are in chemically non-equivalent environments. Of course, this is a relatively small molecule, so there means that there are 3 types of protons. So that's what that tells us. We have 3 different types of protons. All right, and then the 4th thing, and then we're going to elaborate on this in just a moment. You had to do signals, the total number of signals. Then we needed to do the integration, discuss what the integration, my pen is still charging, so we have to use my finger, and unfortunately it's not nearly as neat. What's the integration just like from calculus? Is that area under the curve. And what does that tell you? So for example, in the way that I do it, so that way you can clearly see it, I put my integration here. On the actual computerized spectrophotometer, it's just this little sigmoid curve, and you have to go over to the the y-axis, and I'll let you know. But what does that tell you? This one right here. This 3 means that there are 3 what? 3 protons in that specific environment. So there are 3 identical protons that look like that's what that peak is. Whereas this one has 3 and this one has 2. Okay? And then finally we have this whole idea of the splitting, which the technical term for that was called multiplicity. And it's the one that is the most difficult to explain. Okay, and that's where we go back to that whole idea of the j+1 rule. Where what was j? It's the number of protons on what? On which carbon? The adjacent carbon. Okay. Oh, that's even a way. I've never thought of it. The adjacent carbon. Bada bing. So, if that's what else to, or adjacent carbons, so sometimes you have more than one. All right. So, and we talked about the theory behind and everything, but that This is the hardest one. It actually tells you probably the most important information, but it's also the hardest one to grasp. So let's start putting this in order. And once again, just know those 5 things in order, especially those last 3 are the really important. Always do the RDB, because you'd hate to spend all this time and realize, wait, there's not a ring or a double bond, or that there really is a ring or a double bond. So I'm now going to make this tinier, so we can try to put this into effect. Well, let me bring this up. Oh, it will. It won't let me check the battery, but it's going to let me blow that up. Okay. Oh, and one thing I forgot to put on here on my little thing was the units. So it's delta ppms. And this is a proton NMR. That's supposed to say proton. Okay. So let's start trying to piece this all together. Remember, we don't see carbons, we don't see oxygens directly on this. We only see hydrogens. So we're going to start right here. We know that there are 3 identical hydrogens. So let me see if my pen is now charged it up. I'm telling you that it's just not charging. It's supposed to. I'm going to have to try to get another stylus of some sort. Okay. So that means if we look at this one right here.
Sorry, your request couldn't be processed. Please try again later.
Consuela, did I say hello? No, I did not. She's not even an iPhone. So she's not Siri? Why is she getting upset with this one? Which the fun part is having Consuela and Lola talk to each other. Lola's my car because it's got Bluetooth, and this has got Bluetooth, and so they answer each other. They get upset because if you try to use your phone through it, then sometimes Lola hangs up on her. She says goodbye, and I'm telling you, there's something going on. It's possessed. All right, I just can't say hello. Well, I gotta be careful. I can't say hello, Lola, in the car, and it comes too. But whereas I can sometimes on the phone. Obviously, something I said sounded enough like her name that my phone decided to go off. And she doesn't know the answer to this. Hopefully, you do. Okay, so the whole idea is if we look at this carbon right here, I'm sorry, not this carbon, that signal right here, it shows us that there are 3 hydrogens. I'm going to use this color. They have to be identical to each other. Okay? Now, I already know the answer to this. There's only one way that you can have 3 identical hydrogens in this environment. And that means that they have to be on the same carbon. Okay? And the reason why I know that is because there are only a total of 4 carbons. So there's no other way to have 3 carbons with 1 hydrogen on each. They're all identical. You could try to tinker around with it, but a lot of times, many times, not always, but a lot of times when you see a peak that integrates to 3, that lets you know, okay, chances are, most likely, it's going to be some type of methyl group. Not, like I said, not always. I'm sure that there are times that you can have 3 identical hydrogens and some, which I'm sure we can find one, but it's much more difficult. Okay, whoops, I forgot to put the little, so that's what that looks like. Well, not well, but that's what that looks like. It's a methyl group. We just don't know what it's connected to. So I'm going to draw it like that. Now I'm going to go, let me change color. Oh, it's probably not a good color. I don't know if this color will show up as well. This one right here is going to be the one that I'm going to do in this color right there. Okay. It shows up well on my iPad, but I don't know if that you can tell the difference on this one. So how many hydrogens are in that identical environment? What's the integration? 3. So that means, once again, we have to have 3 hydrogens, which that's a really bad one. And so what do you suppose, what is the one way that we can have 3 hydrogens that are identical to each other? That's a methyl group. They're all hanging off the same carbon. And I apologize that it's why is it now not wanting to recognize my finger? Okay. But once again, we don't know what it's connected to. Remember, each carbon, how many bonds does a carbon make? 4. Okay, that's why I'm drawing this as a squiggly line. We just don't know. Now what you could do is, in theory, you could say, okay, can I connect those two squiggly lines together? The answer is no, because it's ethane, and we know we still haven't used, which I can't show this on the, I don't have enough room on the iPad, but a lot of times, especially when I'm doing something that's more complicated, I literally write out, okay, C4, HAO, and I say, so far, I've used up 2 carbons, and I've used up 6 hydrogens, and 1 oxygen is left. Okay, so that means I still have 2 carbons, 2 hydrogens, and oxygen. We know it's not an alcohol because I already said it's not an alcohol. So now let's go to this third. This one right here. How many hydrogens are in that environment? 2. So let's just draw it like this. But once again, we don't know what's connected there. We don't know what's connected there. But we have 2 identical hydrogens. So now, if I'm subtracting everything, which for those of you who are not here in class and you're listening to this online, you just have to visualize. So I've used up 1 more carbon and 2 hydrogens. So I'm down to 1 carbon and 1 oxygen. That's the only thing that's left. So we now have to start putting the pieces together. And this is where multiplicity comes into play. Because we've got to try to figure out what the pieces are. So I'm going to go back to, I can't tell the colors apart, back to this one. And for its multiplicity, when it split, what did it split into? Is it a singlet, doublet, triplet, quartet, quintet, hextet? What kind of splitting is it? How many little individual, because they're not technically considered peaks, but how many is there? Don't overthink this. How many, what does it split? What does it look like? How many little peaks are there? On this one right here. 3. Okay, so what that means is it's J plus 1 is equal to 3. So therefore, J is equal to 2. Yay, see, algebra is handy. All right, so that means that the carbon or carbons next to it have to have a grand total of 2 hydrogens. Okay, so let's keep that in mind. Likewise, I'm going to go all the way over here to this one right here. And how many little peaks are in that signal? 4. So therefore, it's J plus 1 is equal to 4, and J is equal to 3. So now we can start to put some of these pieces together. What that means is this one right here has to be next door to something that has a grand total of 3. Do we have anything that looks like that? Do we have a carbon that has 3 hydrogens on it? Yes. Now, what we don't know is if it's this one or if it's this one. Okay? Likewise, if I go to this one, it's next door to something that has a grand total of how many hydrogens on it? 2. So, therefore, let's see. Oh, too bad. That would have been too neat. It won't let me do. That means that we can take this one and attach it to this one. So okay, that still leaves this one right here by itself. This one that we have. Let me see, can I move that up? Oh, it moves all of it, unfortunately. Okay, so if we look at the one that we haven't done yet, it's a methyl group, and how many hydrogens are on the carbon or carbons next door to it? How many peaks are in that one signal? And this one right here. Literally 1. It goes up and it goes down. And so, therefore, it's J plus 1 equals 1. So J is equal to 0. So that means that this methyl group right here is next door to something that has no hydrogens on it. So I'm going to go ahead and draw it over here. So we still don't know what it's next door to. Also, we still haven't used up a double bond. The only thing on the board that we have left is a carbon and an oxygen. So where do you suppose that carbon and oxygen goes? In between. Okay, so now then what we do is we put this all together to see if it makes sense. Okay, so I'm going to start, whoops, not that one. I'm going to start here at this end. We have, this is a methyl group. There are 3 protons. Next door, it only has one neighboring carbon. Next door, that carbon has no hydrogens on it whatsoever, so J plus 1 would be 1. So that's this one right here. And it's further downfield than what you'd expect because it's next door to something that's so electronegative. Then we have this carbon here. This carbon has no hydrogens on it, so we don't even see it at all on the proton spectrum. Then we have this carbon with its 2 hydrogens, so that means we have to have something that integrates to 2, which we do. And it has 2 neighboring carbons. One's got 3 hydrogens, one has 0. 3 plus 0 is 3. That's J, so J plus 1 would be 4, and so lo and behold, it has 4. Then finally we have this one, which is a methyl group, which we have this as a methyl group, and it has to be next door to something that has 2 hydrogens. So this one, and you're going to find out this is called butanone, but it does, it fits. All the pieces fit in there together. So that's why you just have to take it in that order and practice. Practice, practice, practice. So let's just do a couple of examples, a couple more examples. Go with not what I was wanting to do. This time, I'm going to give you the compound, and we're going to do the spectrum. Okay. That's a benzene ring. Here, let me undo that one. A benzene ring, whenever it looks like a hexanet, but in reality, it's a cyclohexyl ring that's got alternating double bonds and single bonds. And I'm deliberately making one that's hard or harder. That's an oxygen. So there's the compound. At this point in time, you should be able to recognize the functional group. So why don't we review that too? What functional group is this right here? What functional group is that? It's an ester, because it goes, there's an R, O, carbonyl group, R. Or if you have to think going backwards, it'd be R, carbonyl, O, R. Okay, and this is just a benzene ring. Okay? All right, so I'm going to give you a moment to go ahead. I want you to start working out and try to draw the spectrum for it. And we'll start working through this. All right. So one thing that I suggest that you do, especially until you get used to seeing it, is go ahead and start putting in the hydrogen. Don't feel alarmed to put in hydrogens. These are not methyl groups. These are just hydrogen. Oh, let me just change the colors on those. Each carbon off that benzene is going to have one hydrogen except for the ones connected to the carbon. And then we have 3 over here. Okay, those are not methyl groups. Those are all individual hydrogens. I just put it in a different color. All right, so now what we're going to do is let's start comparing. If we look at this carbon here has 3 hydrogens on it. Are there any other hydrogens anywhere else in this compound that are identical to these? No. Okay, so we know that it's going to be a methyl peak. Okay, now the next question is that, and then I'm going to look down here, and then we have this carbon here, which has, first of all, this carbon has no hydrogen, so that we don't have to worry about anything off of it. Of course, this oxygen has no hydrogens, and this oxygen has no hydrogens. This one has 2. Okay, now, are there any other carbons that are going to be identical, that have identical hydrogens here? The answer is no. Because remember when you do the substitution for the naming, which you don't know how to name esters yet, but if you put a chlorine here instead, that's different than if you put a chlorine there. Okay, so these 2 carbons are different in that sense. Chemically, those are not the same. Not the same. Now, one thing that you're going to find out is on a benzene ring, for the most part, if it's this is called a monosubstituted benzene ring, meaning only one of the hydrogens has been replaced. This one will be a single peak for most NMRs, okay? It's going to be a single peak in how many hydrogens are hanging off this benzene ring. 5. Okay, which in reality, these 2 are slightly different than these 2 versus that one. But usually when we talk about a monosubstituted benzene ring, it's 5. I'm going to actually start with this benzene ring here. And for those 5, do you think they're going to be downfield, like really far away from the TMS signal, or do you think it's going to be really close? Do you remember? Do they tend to be really de-shielded and be downfield, or do they tend to be really close to the 0? No, they usually tend to be pretty far downfield, okay, because of the way that it is. I mean, in the sense that it's not as far as like a carboxylic acid, but it's not going to be like the methyl group. That's what I'm trying to get to. Methyl groups are really, really close, and it doesn't matter to me where you put it. It's probably not that far downfield. But I'm just because of the fact that I'm using my finger. Okay, and we already said it's going to integrate to 5. Notice that I drew it as a singlet. And the reason why I did, and it doesn't matter, we can pick any of these. Let's pick, let's see, how can I say? These hydrogens here do not split themselves. They don't do the J+1 rule. So remember I said there are a couple of special signals that I want you to know. One of them has to do with the benzene ring, or cyclic ring that has 5 hydrogens on it. Because typically it's going to have a single peak and it's going to integrate to 5. So if you ever see that, you should immediately realize, okay, it's going to be a monosubstituted benzene ring. Because it's hard anyway to try to get 5 identical hydrogens. So that's one signal. On the other extreme, we have the methyl group, right? Methyl groups, if you compare a CH3 group versus a CH2 group, which one is going to be closer to 0, a CH3 group or a CH2? CH3. And so now if we look here, we already know that it's going to integrate to 3, right? Because there are 3 hydrogens that are identical there. What will its J+1 equal? So what you're going to do is you just look, how many carbons are adjacent, or are next door to this one? Just 1. How many hydrogens are on that carbon? 0. So 0 plus 1 is 1. And so we would just put a peak there. It's going to integrate to 3, because there are 3 identical hydrogens. Now comes the hard part. Is we have the last 2 sets of hydrogens. We already know they're both going to integrate to 2 because each one of them's got 2 hydrogens on it. The question, and let me change colors so that way we can tell the difference. So those hydrogens versus these. Was that blue and green, I think? Okay. They both are going to integrate to 2 because there are 2 hydrogens on each carbon that are identical to each other. The question is, which one's going to be closest to 0, or closer to 0 since we're having 2 things? Is it going to be the blue or is it going to be the green? The green. Okay, most likely, and this is whenever I would ask you to draw this yourself. I always, on a quiz or an exam, not on the ones online because I can't change those, but the ones that are in class, I would ask you to always explain your logic. And the reason, why is it that the green are, I don't know if it's easier to explain why the green is closer to 0 or the blue is further away. I would personally find it easier to explain why blue is further away. Why is blue further away? It's directly, the carbon is directly attached to an oxygen. Remember, oxygen is really electronegative, so since it's so electronegative over here, it's making these even more de-shielded. The electron density is pulled away. This is pulling away electron density as well, but not as much as an oxygen, since it's directly attached to that oxygen. Okay, so now the question becomes, if we look at, if we said that the green one's going to be the one closest to 0, now let's look at its J+1 rule. How many carbons are next door to it? 2. We have the one that's in the benzene ring, and we have the blue carbon. Well, what will be the blue carbon if it was blue? Okay, how many hydrogens are on those 2 combined? Just 2, because this benzene ring one doesn't have a hydrogen. I've seen people accidentally forget and think that it has one, but it doesn't. So it's 2, and then J+1 would make it, what would this one split to? Since there are a total of 2 hydrogens on neighboring carbons, what will it split to? Split into, I don't want to say split TWO. How many little peaks will that one signal have? 3, because it's J+1, and J is equal to 2, so 2 plus 1 is 3. Okay, so it's going to look something like this. Right, and then last but not least, we have the blue carbon, or the hydrogens on the blue carbon, I should say. And how many little peaks will it split off into? So how many hydrogens are on all the neighboring carbons combined? 2, so J+1 would be 3. So it's also going to split off into 3. You've got to practice this over and over and over and over again. Once you do, it's not that bad. And like I said, these are like little jigsaw puzzles. But just to review, this one is 5, because we have 5 carbons, 5 hydrogens hanging off of that benzene ring. And they just don't split each other. And the reason why I think that the theory behind it is due to the resin structures that are on it. But I would never ask you the theory behind it. Okay. Then we have, and it's fairly far downfield. It may not be, it may not be the 8 area or whatever where I drew it, but I'm just looking for the logic for the placement. On the other end of the spectrum, we have the methyl group. Methyl groups tend to be the ones that are furthest upfield, closest to TMS. It's going to integrate to 3 because there are 3 hydrogens there. Every methyl group is going to have 3, and it's directly next door to a carbonyl group, which has no hydrogen. So J+1 is 1, so that's why it's got that. Then we have these 2 carbons here, and they look identical, but they're not quite identical. One of them, they both have 2 hydrogens on it, so that's the same. But the reason why they aren't is one of them is directly attached to an oxygen, while the other one's only directly attached to a benzene ring. They're both going to integrate to 2, and they're both going to split to 3. Okay? However, it's just the fact that the one that's directly attached to an oxygen is going to be a little further downfield than the other one. All right. So let's do another example. Now I'm going to draw, that's a benzene ring, I just don't want to draw out the individual double bonds. And just because my handwriting is really bad, trying to use my finger here, I'm letting you know that that's an aldehyde. A lot of times I would just use the little stick method, but I'm afraid that if I use only the stick method, you wouldn't be able to tell what it was. Okay. And just in case you can't tell, that's an oxygen, a carbon, and a carbon. Hit record. There are 4, and 1,4-disubstitute benzene ring. They're fairly far downfield, just like a lot of the ones on benzene rings themselves. But they have a very special pattern. They always integrate to 4. But they look like, I call them vampire fangs. Plus, I figure that that's appropriate for this time of year. People usually remember the vampire fangs. They look like this. There's a space between it, and like I said, it always integrates to 4. So I'll put that in. And then I want you to put the other ones in with respect to that benzene ring. Which set of hydrogens, first of all, how many other groups of hydrogens are there total? After we took out the benzene ring one? 3, okay? And none of them are identical. I mean, they're all 3 chemically non-equivalent, technically it's called 3 chemically non-equivalent environments. Which one's going to be closest to TMS? The methyl group, okay? And I'm going to just give it this color right here, okay? And it's going to be integrate. What number will it integrate to? It's going to integrate into 3. Now, what will it split into? Is it going to be a singlet, a doublet, triplet, or a quartet? Triplet. Okay, because how many hydrogens are on the carbon or carbons next door to it? 2. So 2 plus 1 is 3, so it's going to be a triplet. So it's going to look like this. Maybe it won't look that beautiful, but it's going to look roughly like that. So we only have 2 left. We have, it's called the methylene group, the ch2 group, and we have the aldehyde hydrogen that's left. Okay, which one is going to come next closest to the TMS? The ch2 or the aldehyde? The ch2. Okay. In fact, if you remember, aldehydes and carboxylic acids are way down there. Okay, and so it's going to be in here. I'll do it. It's this one. And how many? So the hydrogens on there. The peak for that one is going to integrate to what number? To integrate to it. 2, because there are 2 of them. So I'm just going to put it here. Once again, this is not drawn to scale. Now the question is, what will it split into? Is it going to be a singlet, doublet, triplet, quartet? What? It's a quartet. And we know that because how many hydrogens are on the neighboring carbon? 3. And 3 plus 1 is 4. So it's going to look something like this. Whoops, that's a really bad one, but hopefully you get the idea. Okay. And then finally we have the aldehyde. The aldehyde, I'll just put in this color. So it's this one right here. It's far downfield. It's going to integrate. How many hydrogens does an aldehyde have? I mean, it's 1, so it's going to integrate to 1. And I'll also let you know right now that they usually don't split. Okay, but that and even this one, the J plus 1 is going to be 1 anyway. So it's going to look something like this. So that's that. Now on the board here, I'm going to go ahead and I'll draw out. I'm trying to find one that would be a good one. I'll try to draw one out that's nice and complicated. I shouldn't say that. Something that, what is it? Okay. So anyone who misses class will need